All right, thanks everybody for coming. So today, our guest speaker in the TV Tech Talk series is Aaron Harsh from Rentrak. He's been with Rentrak for 12 years. Rentrak's a company in Portland, Oregon that has a variety of businesses that seem to center around gathering and processing and making useful large varieties of data. So they have a product that works on box office rentals, box office visitors. They have a product that works on movie rentals, and Aaron's going to be telling us a little bit more about that. So he's a senior product architect at Rentrak. He's been there for 12 years. Word is that he's responsible for every successful product they've ever shipped. He is also a victorious poet. He won a competition in 5th grade for poetry. So at the end, question and answer, maybe he'll share some of his verses with us. So without further ado, Aaron Harsh is going to tell us about data processing and how to use it.
Thanks, Jeff. Jeff, thanks for that magnificent introduction. Before I get started talking about the technical side of what it is we do, I'd like to give you a little bit of background about Rentrak's history, just so you can kind of understand our motivation for some of the things we do and some of the problems that we've seen and how we approach them. So Rentrak started out 20 years ago as a home video distribution company. That's the wrong slide. First, let me say Rentrak started out 20 years ago, public company, traded on the NASDAQ under the symbol RENT in beautiful Portland, Oregon. Portland is famous for the magnificent Rentrak headquarters building, for Mount Hood, and for the best beer in the country. And we started out our original business model, which is still active today, was back then videotape distribution, nowadays video and DVD. And our niche was that instead of selling videotapes to video stores for $50 or $60, however much it was back then, we would ship them to them for a nominal handling fee and then take a portion of the revenue for the first several months. So if you wanted to get 500 copies of a movie in so you could have an in-stock guarantee, you weren't spending $10,000, $20,000 getting this in. And if it was a huge doggone video, you didn't lose your shirt. But a side effect of this was that we had to interface with all the point of sale systems to collect the video rental data, so that we could track it, see how much money the video stores were making, how much of it was off tapes we sent them, and how much we needed to bill them for at the end of the billing cycle. So we built a framework in-house for doing this, and then someone on the board of directors had the brilliant idea, as long as we have this information, let's make it available to the studios. And so we built a system, we called it Home Video Essentials, that does this. And here's a sample screen for that. We're looking at DVD revenue this year versus last year. And you can see, it's about the same. Maybe we're down a little bit this year, not too much. And like all of our systems, Home Video Essentials is targeted at a small number of simultaneous users. The end users here aren't just the general public. These are senior executives at movie studios. But the kind of queries that they're running on the system, the kind of reports they're asking for, scan through large amounts of data. And this becomes really important for us later on. So Home Video Essentials is the only product like this. We're the only company that has this view into what's happening at the video stores. And so the studios ate it up. They loved it. And the board of directors decided that maybe this was Rentrak's real business. Rentrak's business was not shipping videotapes. Rentrak's business was supplying business intelligence to the entertainment industry. So we started looking for other places to do this. And the first place we went was the Theatrical Box Office. We found some people that had some executives that had a lot of experience in this industry, that knew all the key players, all the theater chains, all the movie studios. And they explained to us how the industry works and got us some data feeds. We started working on this system in September 2001. And in the first couple months of 2003, then we'd signed on 8 of the 9 major studios as subscribers to our system. And just like with home video, small number of users, large amount of data. And also interesting here is none of these reports are pre-generated. This is all built as the user requests them. And the business rules are such that you can't pre-generate them. If someone from 20th Century Fox logs in, they'll see a slightly different view than if someone from Buena Vista logs in or if someone from AMC Theaters logs in. So theatrical was a huge success. And we started setting our sights on television. And to get started, we thought we'd go into on-demand. And if some of you aren't too familiar with the television industry, right now it's undergoing a lot of changes. There's the traditional linear television that we all grew up with. You turn on the TV, channel 8 is showing something. If you don't like it, you change the channel. But nowadays there's options. There's on-demand, for instance. So your digital cable or IPTV operator might have a large library of content available for you. Whenever you feel like it, choose an item for this content, maybe a music video, maybe a movie, maybe last night's episode of The Sopranos, click play. It's streaming down to your set-top box. You're watching it right there. So we built this system, and it's also a huge success. We have 60 networks subscribing to our services now, and we're collecting data from a dozen cable operators. And on-demand was really interesting for us. It was different than the other systems in a couple ways. The first way was that the data is at the consumer level. This isn't, on the box office side, we'll get information from a theater that says, we sold $500 worth of tickets for Spider-Man last night. On the on-demand side, we'll get information that says, Aaron watched The Sopranos episode 57 at 8:13 last night. And he fast-forwarded 3 times, rewound twice, paused 1 time, and watched for a total of 48 minutes before he stopped. And so this enables us to do a lot more analysis than we could do on the other systems. And our customers really depend on us to do this analysis. We do, for example, we'll give someone a report that lets them see what's the overlap between these 2 titles. How many people that watch SpongeBob also watch The Sopranos? Or how many people that watch The Sopranos are new to on-demand, that have started using on-demand just because they want to watch The Sopranos, as opposed to being long-time on-demand users that just started watching it when it came out. So fantastically successful system, really gave us a foothold in the television industry and set us up for the next project. So my current project is linear television essentials. Here's a screenshot from our demo system. Here we're collecting information from set-top boxes, from digital cable subscribers, from satellite subscribers, from IPTV subscribers. System's still in development, so this is all demonstration data. None of this is real, but the back end is there, and we've actually, on a small scale, built a system that can handle this, that can build these reports for us. Is actually showing populated reports that let us track second by second how many people are watching this program. Do they change the channel when the ads come on? Do they leave when a gory scene comes on, or are they even more likely to say when a gory scene comes on? And this system is also a large amount of data. And I'll talk about the scale later on, but it's something on the Google scale, we'll say. So this is my explanation of Rentrak. But last week, one of the Wall Street analysis sites did a story on Rentrak. And this is what they had to say for us. Let's see if the speaker's working here. Ooh.
Hollywood studios.
All right, let's try this again.
And in early 2003, Rentrak inked a deal to be the data pimp for almost all the major Hollywood studios.
So they called us data pimps. And I don't know that that's necessarily inaccurate, but we say that we provide business intelligence to the entertainment industry. So if you're going to sit down and build a system like this, to collect data, report it back to someone else, then you might be forgiven if you think, what I'm going to do is I'm going to take this data, load it into a relational database, and write some SQL to pull it out and populate some reports. And there's a lot going for that approach. Relational databases today are very mature products. They're about as fast as you could expect something like that to be. They gave you a lot of confidence that the data is going to be there, that you're going to see a consistent view of the data. They do a lot of fantastic things, but there's a lot of problems with them too. And the 2 problems that we saw, first one is that databases, the API, in particular I'm talking about SQL here, this is what almost everyone uses when they're working with a relational database. SQL is, I think, too low level to efficiently develop against for a large system like ours. But on the other hand, it's too high level to get the kind of great performance that we really need on some of our systems. And I'm not going to go into great detail on why the relational databases are like this, or what could be done to change them. Instead, I'm just going to give you kind of a case study of the problems Rentrak saw and how we went about addressing them. So when I say that they're too low level, one problem is that these queries are necessarily tied to a database schema. You have to predefine your tables, views, stored procedures, and then your queries need to know about all these things. And one of our systems will have 100+ reports on it. If every one of these reports needs to know about the existence of a table, this makes it difficult to refactor the database, makes it difficult to do, or either for performance or for maintainability. And there's not a lot of ways to abstract this out. We have views and we have stored procedures, but that's it. And both of those are really useful at some level, but they're really not the end all in terms of building a truly maintainable system. But on the other end, it's just too high level to get us the kind of performance. And a lot of this, I think, is the fault of SQL. SQL is a fantastic language. We get a lot of benefit from it. But it has difficulty expressing a lot of queries, a lot of things that are useful to the business community. In particular, it's not particularly easy in SQL to express a query that gives us kind of customer level analysis that we're interested in. How many of these people also did this, or how many of these people are new, or this kind of thing. Besides SQL, relational databases want full control over how you get at the data. They want to be able to make the final decision about which tables are accessed in which order, which indexes you're using, how it's going to go about doing it. And they almost all store their data in records, which are not a particularly efficient way to store the data. So we've handled this in two different ways. The first one is to put an abstraction layer on top of SQL. So we've increased maintainability by putting something on top of relational databases API that lets us program directly to what we consider to be the problem domain. And underneath the relational database, we've added code that lets it do the kind of analysis that we're interested in, this consumer level analysis, much quicker than you could do if you trusted the relational database's plans. So this layer that we put on top is essentially a translation engine. When we build a report on one of our systems, we'll say, we would like to show these pieces of information. These pieces of information were defined by the developers in response to talks with the end users, them explaining to us, we calculate this metric as follows. We'd like to see this piece of information. After this, we build a translation engine that knows about all this, knows where the data comes from, knows how to calculate it, and then takes the definitions of our reports defined in terms of the business logic and spits out SQL, or for a system that maybe SQL isn't appropriate for, spits out code directly work with data on the file system. To handle the performance problem, then we've linked in our code directly in the database to handle all the real heavy lifting. On our side, all our really large projects are using Postgres as the back end. And we're using Postgres because you can write your own code, you can link it in, load it directly into the server's address space. You can work directly with the data on the records without a lot of overhead and do a lot of high performance tasks without too much work. It also lets us handle queries that are difficult to express with SQL, but straightforward to express in C++, for instance. So here's an example report. This is from our video on demand reporting system. This is showing us total number of orders for each network on demand, and it's got a couple other metrics that make a lot of sense for the business users in that community. I don't know if they make so much sense to us. So we want to see total number of orders, total number of different programs, number of different subscribers that watch that, and the average time that they spent watching a piece of content on that network. And you can see along the top of this that we've got filters that the end users can use to customize this. And because we're letting them change what geographical region to show, what type of content to show, or what date range to show, then we can't pre-generate this report. This has to be built at runtime, interactively, while the user, as soon as the user clicks go. So here's the SQL that built this report. And this was automatically built by our translation engine. Most people would, I think, probably build this by hand if they're using a relational database. And it's not too bad. It's about 15 lines maybe, and it's mostly understandable. If I was going to build a system that only had a couple reports on it, almost certainly I would write some SQL like this and just pull the database, or pull the data directly out of the database. And people do that all the time. But there's some problems with it. I think the first one is that I've really backed myself into a corner about how the data is arrived at. In the first place, I've explicitly specified where the data comes from. Every arrow here points to a spot in the database where I've explicitly specified this table has the data that I want. And there's two problems here. One of them is it keeps me from doing refactoring without having to also change all my reports. And the other one is it's a performance problem. For performance reasons, I might want to put my data on several different tables and dynamically choose, based on the query, based on the user that's looking at it, based on the parameters that they chose when they wanted to look at the report, dynamically choose which of these tables to pull this from. Because I'm explicitly specifying this in the SQL, I can't do this. And the business logic is spread out. I mean, with one query like this, 50 lines, then it's not a huge problem that It's not a huge problem that any particular point on the report is coming out of several different spots in there. But I've got hundreds of reports in my system. I want to make sure that everything is maintainable as possible and make sure that it's obvious to someone looking at the code that this builds exactly the type of data that I'm interested in. So for example, this order rate column, third from the right, is actually defined in several different places. I've got a formula in this outer subquery. I've got something in a subquery inside that. I've got something in a subquery inside that. I've got this whole section down below that I'm joining with, which is there mainly to process that order rate column. And then I've got a join down there below, explicitly specifying this is how you should join these tables together. This is what you need to do to calculate that one column. And then I started filling in the rest of these things. And I got about 80% done with it, and then dinner was almost ready, and it smelled really good. And it was, I mean, it's kind of boring to do that, to tell you the truth. So I stopped doing that. So here's the code. This is actually from Rentrak source code base. This is the code that we use to define that report. I don't know how many people can read this in the back, but basically what I'm saying is I want to see the name of the network, the number of orders, the total number of titles that had transactions, revenue, yada, yada, yada. Basically one line for every column that ends up on that report. Our translation engine takes this, converts it to the SQL, runs it, builds the report for the end users. And if you flip it on its side, that might be cheating, I'm not sure. But if you flip it on its side, then you can really see that one line in there actually corresponds to one column on the output report. So besides making the code a little bit more obvious, then this also gives us a huge benefit. With a 100+ report, we need to make sure that everything is consistently handling the same business logic. And on our systems, there's a lot of interesting business logic. At the very least, we've got situations where we have Hollywood Video and Blockbuster Video, and they're not allowed to see each other's data. And if one of them ever sees any of the other one's data, this is a huge problem. They're both unhappy, and they're both angry at us, and that makes us unhappy. Aside from that, on systems like Box Office, we've got 100 years of interesting business rules. There's sneak previews, which have really interesting logic on how exactly the data is calculated and who's allowed to see it. We don't say double features, actually. We say multi-features because there's triple features, quadruple features. I think we've seen quintuple features out there. And nowadays, 3D is surprisingly making a comeback. And 35 millimeter versus digital is also really interesting right now. And aside from that, we have end users that maybe someone's in charge of all the Spanish print distribution for Box Office. He's not allowed to see the French data. The French guy is not allowed to see the Spanish data. Neither one of them are allowed to see the revenues for the original English version. We have to make sure this is consistently applied. All these rules are consistently applied across every single one of our systems. And especially on the new businesses, on-demand television, or some of the really interesting things that are happening on digital television or IPTV, we get a lot of new business logic that comes in. People are still trying to work out, how to do this. What's going to make, what kind of data can help them give the end user the best experience and help them make the most possible money. So we need to be able to adapt to that quickly, and we need to be able to quickly make these changes across the entire source code base. And even on a system for a really robust industry with a lot of history like the film industry, even though that place has been around for 100 years, Hollywood is a creative town. They come up with a lot of interesting business rules all the time. And they expect them to be followed to the letter and implemented very quickly. And if we had to update 100 different queries, 100+ different queries, different versions of the query for the cable or for the theater chain, different version of the query for this studio, different version for that theater, then this would be a nightmare. Maintenance would be a complete disaster. So, for example, let's say we're going to add a new business rule. And our new business rule is that HBO wants to be able to flag some titles as top secret. And then when Showtime logs in, or any competitor logs in, they shouldn't be able to see the rating or the share for this program. On this particular query, I might need to add a where clause. I'll probably need to join to a new table that keeps this type of information. And the query is user-specific. HBO is going to get a different view of this than Showtime is. And we can handle that just by passing a different parameter to the report. But someone like Comcast or Time Warner Cable is going to get a wildly different version that's not just filling a different parameter to one of the where clauses. But with our translation engine, this is just no longer a problem for us. The problem is solved. We make the change in one central place, teach the translation engine about this new business rule, about when it's appropriate to join in a new table. It's actually all constraint-based. We just describe to it, we also need this piece of information. This piece of information is on these 3 tables. It'll automatically figure out for us, you need to join here, you need to do this. This is how you need to go about calculating this data. It's consistently applied across 100+ reports, put in some unit tests to make sure everything's working fine, and we're done. So, as far as we're concerned, that problem is just completely solved. So you might be thinking about this and think, I should go and I should build a translation engine. I should convince everyone at Google we need to switch to relational databases, stop writing our own file systems or whatever it is we're doing, and then we're going to use Aaron's brilliant idea, start building a translation engine. And I think that, like I said, if you just have a couple of different queries, the last thing you want to do is build one of these translations engines. It's a huge amount of work. We've built it up over the last 7 or 8 years, and we learned a lot doing it. Right now, I think we've got something which is unique in the industry, which is specifically designed for the type of business rules that we've seen coming up over and over again, not just in the entertainment industry, but in some of the other industries that we've worked with. And it's completely indispensable now. So this solves the problem, I think, of SQL being too low level. But we still have this other problem with the database being too high level. And what I mean by too high level, this is the thing about relational databases that I've come to learn over the past 12 years at Rentrak. The thing about relational databases is that they're very, very slow. And we get a lot of data in at Rentrak, and so this is an issue. And let me talk about some of the volumes that we get. So on the box office side, we get end-of-day revenue figures for each of 5,000 theaters. So each theater will say, on Spider-Man, we made $2,000. On Shrek, we made $1,000. And that ends up being about 20,000 records a day. And that's really not that much. But 2,000 of those theaters actually report to us every hour. And that ends up being about 250,000 records a day, which is still really not that much, but let's just charitably call that a fair amount of data. On the home video side, we get from several thousand video stores line item of data for every rental that takes place at those stores. This customer rented this thing for this many days for this amount of money. And that ends up being about 2 million records a day, which is, that's starting to get interesting. And this is starting to get to the point where you need to do something unusual to get interactive response time on big queries. On the on-demand television side, we get about 85% of the North American on-demand data, which, and this is also at the individual order level. This is Aaron watched SpongeBob SquarePants at 8:30 last night for 15 minutes. And that turns out to be 10 million transactions a day. And that's a lot of data. And if you guys weren't Google, I can guarantee you'd be really, really impressed if I said 10 million transactions a day. But you're Google, so I'm going to have to do more to impress you than that. So my current project that I'm working on is linear television tracking and reporting system. And we have performance targets that are arrived at as follows. There are 100 million households in the United States that we want to collect information from. Each one of them is going to change the channel around 200 times a day on average. And every time someone changes the channel, this is going to be a line in a data file that gets sent to us. So by our calculations, that's 20 billion transactions a day we can process. Holy cow. That is a lot of data. So to even begin addressing this, we have to start thinking about what is it that makes these relational databases slow? What are we going to do to make them faster so we can handle 20 billion transactions a day? So the first problem we've got is that records just aren't space efficient. They're just, it's very flexible, it's very convenient, but as far as performance goes, it's not really the best way to store data. And one of the big problems here is first normal form, defined by Dr. Edward Codd 30 or 40 years ago. And this is the idea that every record, or any record, should not be allowed to have a variable amount of data. So if I'm going to store channel changes or program views or something like that, I need to store one record that says Aaron watched The Office at 8:30, another one that says Aaron watched 30 Rock at 9 o'clock, and a third one that says Aaron watched Scrubs at 9:30. And when you've only got 5 records, then that's not really a problem. But you could, if you wanted to, you could shrink that down to 2 records. One for me that keeps a track of everything that I watched, and one for Chris that keeps track of what he watched. And that makes our database a little bit smaller for a couple of reasons. One of them is I've got rid of a little bit of redundant information. I'm not saying Aaron, Aaron, Aaron anymore. I'm just saying Aaron. And the other one is that the relational databases are going to add some fixed amount of overhead for every record that they add to the database. And relational databases can actually store data like this. Modern relational databases allow for complex fields like arrays of structures, things like that. But the query support just really isn't there like it is for records. Relational databases want to work with relational data. These arrays are not relational data, and so they're not quite as performant, not quite as flexible. And we've got this other problem that I talked about before, that the queries are not as efficient as they could be. When I'm working with a modern relational database, every time I want data, I get it through a SQL query or a Quell query, or actually that wouldn't be a modern database. And this is great for ad hoc access. It means that my boss, Chris, everyone give Chris a hand, please. So now that I've stroked Chris's ego, Chris could write a query, run it against the database, get some sort of useful results. Looks like English. You probably understand exactly what this query does. But, and the database has a good optimizer that's going to take this query and try and figure out some method, some little scheme for how it's going to actually go about arriving at the results. That's probably going to be pretty good. So he's going to get his data back eventually. In fact, those things are so good that a lot of people actually rely on them. They actually build large systems with large amounts of data and think these query optimizers, all these advancements that we've made over the last 40 years, these are going to save us. These are going to give us a system that can give us lots of data in a very short amount of time. But there's a lot of things that they're not great at. And there's been a lot of work on these things, on these databases over the last 40 years trying to speed these things up. And in the industry and academia, people come up with time series databases. I'm not even going to bother reading all these things. Let's just say that there's a lot of things that people have done. But it seems to me that the big problem is that if you have a room full of smart developers and they know how to go about getting the data, then the relational database is just this big beast that's in the way. It's in between you, it's in between the data. Making it smarter is not necessarily the best way. It's never going to be as smart as the people in this room that have to sit down, figure out what the best way is to get the data. So let me describe a typical reporting server scenario. If we were going to go the total relational database route and try and build on-demand or linear on top of relational database, probably what we'd have is an online transaction processing database. We'd process individual rentals or television views or whatever on this thing. And then every day, every week, we'd do a bulk copy of everything that came in new that day or week over to our data warehouse. And we'd probably hire some sort of consultant to come in, and he'd tell us that we need to put the data into star schema for our best possible performance. Or he might get fancy and say, you guys should really use a snowflake schema. But the real problem here with getting great performance, and I mean interactive performance, where an end user can run a report and get something back before they get bored, is the real problem here is that we've got this big table in the middle. They call it the fact table. And every industry, the facts are different. In our cases, the fact is that someone rented a video or watched a television program or changed a channel. And for something like on-demand, this fact table would have about 5 billion rows in it. And that's just too much. I mean, if you talk to a database vendor, they'll say, absolutely, we can handle a 5 billion row fact table in a snowflake schema. And they can get you reports. They can do something for you in 10 seconds on this 5 billion row database. They certainly can't do any sort of customer level analysis about this guy did this and this and this. And there's a trend among these sorts of people that these sorts of people do this kind of thing. So you need to shrink the data. And if we were willing to give up the information that, if we're willing to lose the fact that it was Aaron that watched SpongeBob SquarePants, if we're okay saying something like, all we need to know is that in Mountain View yesterday, there were 500 different people that watched SpongeBob SquarePants, then we can shrink the database down. And in OnDemand's case, that shrinks the database from 5 billion rows to 300 million rows once we rekey on just day, program, and area. But at that point, you can't analyze the viewer activity. And this is really what our customers depend on us for. This is why we're doing it for them and they're not doing it themselves. So first thing we need to do, take the data out of first normal form. And so that we don't lose the data, once we've taken it out of first normal form, we make the records big and fat, and we store a lot of information on them. We store enough information on it that we can get every data point that anyone's ever interested in, everything we need to know at the consumer level. Once we've done that, we went from 5 billion relatively small records to 300 million kind of big fat records, which turns out to be a lot faster in our case. Then we extend the database with our own custom analytics that know how to work with the data that we stored in these big fat records. That can take this and say, if this big fat record here stores a list of everyone that watched this program, and this one is a list of everyone that watched this program, how many of those people are in common? What's the overlap? Or what's the total unique subscriber count between the two of these things? Update our SQL to use these database extensions instead of using the standard Oracle or Postgres or Sybase or whatever. And then we've got a system that can build these reports relatively quickly. And because we're using our own custom analytics, then the queries are a little bit more difficult to write. But this translation engine actually comes in really handy again. Because we're not actually writing SQL, and we're not actually writing the code that uses custom analytics versus standard SQL analytics, then we're in great shape. It takes care of it for us. All we have to do is explain, this is not how you get this data anymore. This is the new way to get the data. 100 reports are instantly updated and sped up. And the results are absolutely fantastic on this. What we've seen on this is, on OnDemand in particular, is that the average user runs a report. When the average user runs a report, they aggregate the data over 300 million different views out of our 5 billion different view database. And every single one of these reports that they run does some sort of consumer level analysis. Even if it's something as simple as counting the number of different people that did something, they all have to touch the individual consumer level data. Our typical report builds significantly faster than 10 seconds. By significantly faster, I mean probably like 7 seconds. On completely reasonable hardware. And you guys are Google. You're probably thinking to yourself, well, you know, we handle more data than that, and we get our data back in less than 10 seconds. And so you're confused when I say that this is fast. So I think the disconnect here is how we view reasonable hardware. So this is, I think, Google's definition of reasonable hardware. This is a new data center about 80 miles east of Portland, Rentrak's headquarters. And this is about the same size as the town that I grew up in. And it was a real town, too. It had a mayor, they had taxes, we had police, and it was about exactly that size. So here's our definition of reasonable hardware. That's Chad over there on the left, and I think maybe he's not technically hardware. And then he's pointing to on-demand reporting server number 1 and number 2. And those two servers together, there's 2 of them mostly for redundancy. Those 2 servers actually handle all the on-demand reporting traffic for our system. So things are fast. Things work great. Let me show you what the data flow looks like. It looks basically like what you saw before in the data warehouse. The main difference is, actually 2 differences. One of them is that we've got some great logic in-house for integrating the data into our data warehouse every couple hours instead of just every day or every week. And also, when we move the data over to the data warehouse, we summarize it, preparing it for this analytic code, and stick the data in these enormous fat records, which I'm kind of glossing over. In the Q&A afterwards, you guys can try and pull some information out of me about these fat records. And once they're in the data warehouse, then data is available for the end users. They come in the morning, look at last night's data, reports come back quickly. Everyone's happy. On the linear side, though, we've got these 20 billion transactions a day. And that's a lot more data. So the model changes, but it actually doesn't change that much. The database still maintains these big fat records. And the format of these big fat records, the number of them that you need, the size of the fat records, has absolutely nothing to do with the input data. It has to do solely with the type of information people want to get out of it. If no one cares about customer level analysis, you can just completely get rid of this. You can say, I want to store one value, the total number of people that watched it. And then you're going to be perfectly fine with it. It turns out on the linear side, people, the metrics that people are interested in actually aren't as complicated as the ones that people are interested in on the on-demand side. And so we've seen that the end result is actually slightly faster queries and simpler analytics. On the input side, though, then we've just completely abandoned the OnDemand transaction processing database for our input. Instead, we'll get files from cable operators, IPTV operators coming in, process them with some code that reads them, puts them in some compact, very useful format for doing the summarization later on when we put them in the data warehouse in the Never process that does the summarization. And actually, this is another case where the translation engine concept came in really handy, because we have a lot of different views of the data for the linear system, just like we do on the on-demand system. Then there's a lot of code which is working in terms of the problem domain, needs to access the data. And so this right here is some code that you probably can't read either, that builds a view on top of our flat files, prepares it to load it into the database, and organizes the data by network, by day, and calculates all the standard metrics: the total share, the total rating, the number of households, the total amount of time that they spent watching. And you might be concerned that this level of abstraction actually slows things down. But one of the nice things about using this whole translation engine concept is it means that you get to tune the translation engine. You don't have to tune 100 different reports or 50 different views on top of the data. And so what we've seen is that on the linear side, one of those machines that Chad was pointing at, two proc machine, dual core, so four cores total, actually imports, validates, processes, and prepares for quick reporting about 3 billion channel changes a day, which means that we could comfortably handle the North American television viewing on the bottom half of that rack. So, I mean, this is kind of a high-level overview. I'd be glad to go in more detail in the Q&A. This thing, but really, I guess what I'm trying to show you here is that I think it's possible to build a system that's really the best of both worlds, that uses a database, gets you a lot of the advantages you get with a database. You get consistent data, great backup support, ad hoc queries, but lets you still work with a large amount of data and do complex analysis. 5 billion rows available for reporting online right now on our video on demand system, and a system which is capable of handling trillions of rows, trillions of channel changes online, ready for reporting. So that's that.
Do we have a local mic for questions? Yes, we do, right here.
Jeff, if we have a local mic, does that mean that I don't need to repeat the questions?
True, he does not need to.
Can you obviously hit that one?
Any question?
Then you don't have to. He doesn't.
Great. Fantastic.
All right, so why don't you recite the poem you won your contest with?
I don't remember my poem.
Oh.
How many, what is the size of your database
In terms of
terabytes?
terabytes? We actually have, that's a great question. So we have two parts. So we have the online transaction processing. I'm sorry, the question was, what is the size of the database? So we have two parts to this. We have the online transaction part, where we actually store one record per on-demand television view. And then we have the reporting side. Once we've actually summarized the data and have it available for reporting, then we can purge it from the OLTP side. And so we keep that constant at about a terabyte. And the online reporting system is, I think, about 400 gigabytes the last time I looked at it.
How much history do you keep going back?
Got it. So the question is, how much history do we keep? We have yet to purge any information from any of our reporting systems. So the home video system goes back for a decade. Box office goes back, I don't know. We actually, 86. We actually got historical data feeds from some of the studios and theater chains. So that goes back to 86. And on-demand goes back to the beginning of on-demand, which is 2004.
The architecture you described doesn't seem to be specifically tied to the business that you're in. Mm-hmm. There are presumably a lot of other businesses that have very similar problems. Could you just say what your thinking is about that and what those people are doing who are in those other businesses right now instead of using what you're using?
That's a great question. So the reason that our architecture absolutely is completely neutral, and Rentrak has a couple divisions which handle other sorts of data, not entertainment consumption data, and they actually use these tools too. I focused on this just because Rentrak's business focus right now is on the entertainment industry. I mean, eventually we love to collect every piece of information everywhere, just like you would, and report on it. But right now, as we move forward, we're trying to focus on our core competency, which is just entertainment industry data.
So is Nielsen like a competitor of yours?
Nielsen is a competitor to us on the box office side. They actually had a product which is, Chris, what am I allowed to say on this?
I don't think I can say anything.
Okay.
You can go ahead.
All right, I'll give a straightforward answer to this, not pulling punches. So when we got started on the box office project, then one of the Nielsen subsidiaries actually had a monopoly on that market, and they'd had it for 15 or 20 years. Within, like I said, within about 15 months, 16 months of us starting the project, then we had actually taken 8 of the 9 major studios away, and now we have 100% market share on that. So, you know, in one sense they're competition, but in the other sense they're just no competition for us.
So how many fact tables do you have, and how frequent are the schema changes on them?
That's a great question. So, so once we actually put a system in production, then the schema changes aren't that frequent. And once you get to a really large database, then there's kind of a vested interest in, you know, trying to not to make as many schema changes as back when it was, you know, a cute little 100 gigabyte database. But see, so on our system, I guess we'll actually have different views of the data available for reporting. So we'll have one fact table, I mean, a partition fact table, so maybe, you know, 200 partitions. One fact table keeping the detail, either, you know, the individual views, the individual videotape rentals, or DVD rentals. Sorry, I've been at Rentrak for 12 years. Back then there were no DVDs, and so please forgive me if I say videotape. So in this case, we'll have, on the online transaction side, we'll have just one table that stores all this information. As we move the data onto the reporting system, then we'll summarize it in different ways for, you know, for different performance. Like we'll have maybe one overall national view that our translation engine will prefer to use if it can. And we'll have, you know, more detailed views by area, by title, by day that it'll use if it, you know, can't use the national version, just because the end user's not allowed to see it, or because they've selected a list of filters that don't allow them to see the overall national view. And in this case, I think the linear system probably has about 50 of those, and the on-demand system probably has a similar amount, around 50.
So I'll try and pry on the big records.
Uh-huh.
Thank you. So a little bit beyond ones and zeros, can you describe some of the structure that you use to describe this?
I think I can go into a high-level overview of this. So, so really the structure of the things depends on what you want to get out of it. You know, if all you want to get out is total number of orders, you store total number of orders, then at that point you don't need a big fat record. In our case, the interesting metrics on video on demand are the individual people that are doing things, and in some cases, more detailed analysis on it. So it's kind of it's proprietary custom format to Rentrak, list of people that actually watch these things, designed in such a way that it takes not too much space on disk, and that it's actually CPU efficient to do this aggregation later on. But we'll in these, and that actually sounds more specific than it is. We actually do this for all sorts, use the same format for a lot of different reasons. And we actually have 3 or 4 different formats that we use on on-demand and a couple on linear for doing things like tracking, gosh, I'm trying to think of a good example here. Tracking frequent viewers versus non-frequent viewers on on-demand. We can tell you how many people that watched on-demand content last week watched 5 different things versus ordered, you know, 50 different music videos or something like that. But we'll use these same values. They're, you know, sort of specific, but they're also general enough that we can do things like do demographic analysis or, you know, interesting things like that. So that was probably a pretty vague answer to that, but I'm not sure how much detail I can go in on that.
Thanks, everybody, for coming. Thanks, Aaron.